cut me down so we never see eye to eye. It's hard to argue when you're never the same side. You found the lies I built around me, made up some brand new ones about me. Baby, I love the way you're looking in this good light. I love you cause I don't love me. I love you cause I don't love me. I love you cause I don't love me. I don't think I deserve better. This is not even about you. I lost me before I found you. I love you cause I don't love me. I don't think I deserve better, but we deserve better. Sometimes I see a piece of what this could be. I'm terrified to let you go. But if you give me half your heart, I'll never have your heart. Two half hearts don't make a whole. I just want someone to love me. Come on, somebody just love me. I love you cause I don't love me. I love you cause I don't love me. So I don't love you, I don't love me. I don't think I deserve. This is not even about you. I'm alone with or without you. I love you cause I don't love me. I don't think I deserve better, but we deserve better. We deserve better. I know you know the power in your text. Perfectly timed at 1 a.m. Suddenly there's tension in my chest. Feels like I'm running when I'm standing still. You're controlling every part of me with 6 words. The crazy part is that I tell myself it's on hurt. But the truth is, I love you cause I don't love me. I love you cause I don't love me.
Better. That's the song we played before the lecture. So, so this week we have the reading quiz. We only have one reading quiz. So do you feel better? And the reading quiz that we have in this week is mostly about what you should learn when you took your undergrad operating system. So it's more like a review. So does that make you feel better? if that doesn't make you feel better, well, don't take it politically, but you should believe that tomorrow will at least be better. All right. Anyway, so let's start. So today we are going to continue our lectures on the Unix operating system. And if you read a paper or read the textbook chapters, you know there is a set of process API that would help us to manage one of the important abstraction that many operating system has. So that's our process API using Unix. So today we are going to dive into that in detail. And if we have time, we will talk about, we will continue our discussion on the design of Mach as well. But before we start, I know it has been a weekend, especially it's a long weekend. I hope you guys didn't travel somewhere that is like 120 miles away from your the radius of your home. According to California stay-at-home order, you should not do that anyway. So, but I do know that, well, you must take your mind in a status that is in a rest. So you probably don't have the memory what's going on. So again, last lecture we talked about Unix, and it's important that to understand that in Unix everything is a file, and that's actually one of the most important contribution of Unix is introducing the concept of file and make everything like as a file. So some of you might feel like, wait a moment. I saw the abstraction in Unix is based on processes. Well, true or false? So the process is indeed one of the abstraction that exists in Unix. However, process is still under the abstraction of files. If you don't believe, let me show you the demo right now. So let's say like, okay, so there's a program called top, and this program would help you to see what are the process that you are running on the system. And apparently there is a process with number 26996, right? So if you go to the proc, you will find, well, there is indeed a directory of 26996 for the process. So everything about that process, like what are the CPUs that the process can use, and what are the system calls, the service that it can use, the command line, everything that's related to that process is actually abstracted as a set of files under the in Unix systems. So in this way, I hope you are now convinced that even process, you thought process should be the universal abstraction in most of the operating system, but at least for Unix, that's not true. And even for Linux, that's not true, because process is another abstraction under the umbrella of files. So process is an abstraction, that's correct. However, that abstraction is actually based on the abstraction of files. So everything in Unix is actually files. So that's one thing that you should always remember when we talk about Unix, that the file system, the file is the most important abstraction. And we will spend about a quarter of the quarter to talk about the file system after midterm. So for now, just remember that everything is files in Unix, and that's really important. And another contribution of Unix and why it is so influential is because this is the first programming, the operating system with their kernel written in high-level programming language. And because of that, so it's portable, a lot more portable than other operating systems in its age. And because of that, people know that, well, we should have our operating system written in this kind of a language. And again, we said that even for process is still under the umbrella of the file system abstraction. And for each process, now you should know that each process has its own virtual address space, and each process supposed to have its own virtualized processing resource, and that is not shared with everyone and with anyone. And the role of the operating system is to isolate and manipulate the usage of this resource dynamically. So and again, even for the process abstraction is under the file abstraction. And remember, with the process, that's how we got the result of our first demo. So again, so for Unix, how you protect each process, how you protect each file, they have the permissions associated with each file, and that's put in the metadata of each file. We will talk about that later. However, as a summary, they provide a set of features like each file contains 3 types of users, but in the original paper, there are only 2. And this shows you that Unix is a moving target. It changes all the time. And each type of users have different permissions. And there is also another spatial permission called setUID that can promote write amplifications. So through the last lecture, the blue and red team, you guys are really close. And today we are going to continue talking about Unix, and we are going to, hopefully we can get into Mach. So we said that, well, under the file abstraction, file system abstraction, when you run a program, the running program will become another abstraction called processes in Unix. And Unix has 4 basic process API that you should at least know. The first one is fork. The second one is wait, and then execute. There is a family of execute and exit. So the fork is a function call that will definitely kernel will involve. And what does the fork do? What does the fork do is that it will create a new process. By create a new process, it means that the new process will have its own virtual address space that is isolated, separated from other people. But Unix has the concept of children and parent. So and remember that when you are a newborn, you must inherit something from your parents. So what the child process inherits from the parent process is that you will get everything from your parents' virtual memory address space at that time. So whatever your parent memorize in their memory, you will have it. I hope human beings can have that kind of capability so that I can skip a lot of elementary school or high school. But unfortunately, human beings are not like that. But in operating system, we can create things like that. So in Unix abstraction, when you create a new process through fork, you are actually get everything identical and make a copy. Right here, we say copy is not linking, it's copy. So you have a separate copy of the parent's memory. And then at that point, you guys are isolated and your own memory will evolve as your program executes. So the fork process is actually a very, fork function is a very spatial function code in a way that when you call it once in a parent process, it will return twice. One time it will return in the children's process, in the child's process as 0. And the other is that it will return in a parent process after you fork the child process. And in a parent process, you will receive the the child's process ID. So that's the fork. So knowing the basic about the fork, yeah, I know it's coming so soon, right? But I still want you to, but I assume that you already know this. So why don't you spend 90 seconds to think about, go into this code snippet and let me know what you think about the outcome. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what I learned from you, definitely we will need some kind of discussion within group. So now open the file that I sent through the chat and go into group discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now look at, well, so now I am inviting one of the group to share your thought with us. Okay, I have Xin Nan. Which group are you? Okay, looks like it's a blue group.
Yes, I'm in team blue, and
okay.
our answer is A.
So I'm just curious, like how many guys in blue teams are you like a gamer? Because I always feel like the blue team, you have like faster mouse click speed. Anyway, okay. All right, keep going. Okay, your team's thoughts.
Yeah. We think we think the answer is A because I'll explain it. First, the number of times my PID is printed should be 1 because
and the reason is
because the if statement in line 3 is executed and goes to line 4 for the child process. Because
so only the child process would get this
yeah.
line executed, right?
Yeah, because fork returns 0 for the child process. So
So it's the child process would print this one, right? So
yeah,
then you would get the value of 7 printed as well, all right?
yes.
And the parent process won't print this line.
Yeah. And we think the number of times child PID is printed should be 2 because the child process does not execute EXEC. So
Mhm.
both of the parent and the child will execute the second print or F statement.
Mm-hmm. Okay, so another way to think about this is because when you use fork to create a process, you are actually duplicating your process. And when we say duplicating, it includes the data you duplicated. Also, remember in von Neumann architecture, all the instructions are also in the memory. So the instructions are also duplicated. Your program counter is also duplicated, right? So whatever in the original program will continue execution on both duplicated process, and unless one of them is trying to change that, right? So and for the parent process, because the PID we receive here will be 0. So so there won't be 2 printed here because the parent process would got its PID assigned as wait. Sorry, the child process will get its PID set as 0. So the child process will print 0, and the parent
Yeah.
process will print the child process PID, which is 7. So in this way, only the first one is correct. Okay, thanks a lot for Xinan's sharing. For those of you who still have your hand raised, if you have no question, please put it down. Okay, cool. So we are good, right? So okay, 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 cool. So now so let's go through the fork process one more time in case you are not still don't quite understand what's going on. So before fork, that's our parent process, and the PID is initial. It's just initial. We just allocated a register for it, but what's the value inside is undetermined. And when you call fork, right, what happened in fork is that we will duplicate the same virtual memory space. So you will see 2 copies of code, 2 copies of the static data. You will see the same stack and heap data. And then both processes will start executing and from the same PID, from the same program counter. And as we said, on the parent side, the PID will be assigned to the child process and process ID. And on the children's side, on the child side, the PID will be assigned as 0. So knowing this, right, you will see that one of them is now 7, the other is 0, right? And keep going because only the child process will got the 0 values in this if statement. So you will get the PID your current PID 7 printed. And on the other hand, if you're on the parent side, that one won't get printed. So that's why you will see the output will be like this. So that's what happened when you call the fork. Okay, so for this problem, it's great that after discussion, everyone agrees, almost everyone agrees that the answer is A. So if you look at before discussion, well, A is popular, but a lot of you still don't agree it's A. And after discussion, most of you think it's A now. So which is an evidence that you guys did a discussion, and that's really great. So now let's introduce knowing the functionality of fork. And let me bring one more function into your mind. That's called exit. So exit will free the resource and terminate the process. So a process calls exit. It will flush and close all the open files and stream, release the allocated memory, and its own process will be removed from the kernel data structure. And it also passes a status to the parent process if the parent process is waiting for that. And if there's nothing wrong, you will by default you are going to pass a 0. as the return value. So that's why in a lot of cases, like in a lot of functions, we tend to return zeros if nothing goes wrong, because you are going to return that all the way through the end of your program, right? So now, okay, knowing that that's what access is doing, again, we are going to test if you know what would happen if we add an exit. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, we have a pretty high consensus on an answer. So I'm going to skip the group discussion, but I'm still inviting one of your group member to share your thoughts with us by raising your hand. Okay, so I have Rogelio. I saw you raise your hand first. Would you mind to share
Sure.
with us?
Yes.
So you are in, right? Okay.
Team Red. The exit function, as it states here, terminates the process. So therefore, the child process does not print the last print statement. And so we only see one.
So everything that has 2 here should be eliminated, right?
Sure. Yes, that's correct.
And how many times the my PID is printed?
Once.
Once, right?
Yes.
So it only leaves E as the only answer, right?
Right.
So do you agree that here we are going to print 7 and here we are going to print 7 again?
Yeah.
Okay, so here, well, so thanks for Rogelio, right? So, and so the answer is indeed E. So, looking at what you shared here, right? Most of you agree it's E. So there are still some of you don't quite get it. So didn't quite get it. So let me walk through this example real quick. So hopefully that will convince you, right? So, okay, so first of all, in the very beginning, we said for fork, right? What we do with fork is that we duplicate everything in the memory. So whatever in the parent will go into your child, and then after calling the fork, the parent side will be 7. The child side will be 0 with the return value assigned to the PID, and only the right hand side fulfill the if statement here. So the right hand side will print my PID is get PID, which is 7 here. However, after printing this one, it will exit. So the program will terminate and vanish from the system. On the other hand, your parent process will keep running and print that your child PID is 7. So the answer for this question would be E by walking through this example. So now, well, what a fork. We are going going to see more forks. So looking at this pieces of code, can you tell me how many animal noises will be printed? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what I learned from your result, I would suggest us to have a very short discussion, probably 1 or 2 minutes, and so that we can synchronize the result a little bit. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so, well, put your hands down, put your hands down. All right, so after discussion, I believe we do have an answer that everyone agrees. So raise your hand. Okay, I got Jolene. So why don't you share your thoughts with us? Well, your group's thoughts with us.
In our group, we think the answer is D, 14.
And why is 14?
The first fork is there are gonna be 2 process, and the second fork will be 4, and the decimal will be 8. So 2 plus 4 plus 8.
Okay, so on the other hand, maybe we should say this, right? When you fork the process, everything here will be duplicated for 2 times, right? So this will have 2 times, and this one will have 2 times, this one will have 2 times. However, when you have a fork here, everything here will also have 2 times again. So 2 times, 2 times. And when you fork here, you will have 2 times, 2 times. So this is 2, this is 4, this is 8. So everything will be 14. And thanks for the blue team to share, right? And if you still don't trust this kind of analytical analysis, right, it's very easy for you to write a program, right? So let's run the program and see. Well, I hope I have this demo. Okay, 202, and I have the process API demo, and okay, so noise, right? So this is the noise program. As you can see, is exactly the same, except that I add the PID out of it, so you know how many processes are executed. So now, if I try to run the noise program again, you will see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 has been printed, and you will see that, well, there are quite a few, so there are 4 processes. Each individual process would print an oink, and from 392 to 399, everyone will print ba, and only the first two, 392 and 399, will print mo, right? So that's actually telling you what's going on here. All right, so Chi Chu, do you have question? Okay, no, okay, cool. So now let me, so it looks like you have a lot of you have most of you have I would say all of you have very solid background for undergrad operating system, which is probably the best ever result I had in this question. Great, so you guys are really doing so great on this one. So now let's go through one more API, a set of API that's execute. And within execute, one of the most frequently used one is the execute VP. So this one will receive arguments like what's the program you are going to use to, so first of all, what's execute? So the execute is stop the current process. By stop, it means that we are going to reset the program counter, and we will overwrite the process address space with the new program and the new program that you are going to load here. And here we have the character array, meaning that you are going to receive the program from the file system. So this program is a descriptor to the files that you want to load as the new process. So here, right, another evidence that even for processes, it comes from a file. So and then with the current process address space being overwritten by the program you specified, we will use the argument, the set of argument specified here to run the program and insert the process into ready queue for execution again. And the thing is that the EXECVP program won't create a new process. So now, some of you might be curious, right? Why we have fork to create a new process, but has EXEC to create to rewrite the virtual address space. And the only reason is because we want flexibility. And there's not really a right answer if you should do either way, because you can definitely has EXEC instead of fork plus EXEC. But what Unix is trying to do is because they want to be flexible, so that sometimes if I just want to duplicate the process, I can simply do that. But if I really want to rewrite my virtual address space, I can still use exec. However, if you only have exec, you are not able to have the feature that fork provides. And another thing is that with fork and execute, that would allow the Unix system to easily support redirection and pipe features. So by redirection and pipe features, for those of you who are not very familiar with Linux or Unix, is that in Unix you can use greater than or smaller than to redirect your output to another file, and you can also use pipe to use your output as the standard input of another program. So those are the features that you won't. Those are the features enabled by fork, and in the so in the last lecture, we mentioned that shell is not part of the Unix kernel. And indeed, you can imagine that, right? With fork and exec, both are user space API. And this user space API will help you to switch the current process to the kernel mode. However, you can write a user program that invokes this API to create a new process when you want to execute a new program by using fork and exec. And the rationale is this: first, you fork a process and then set up an appropriate environmental variable before you call exec and use that as the exec. And if you want to redirect your output to a file, you can potentially do this by duplicating your file descriptor, and that's very difficult to achieve if you are using Windows, because the Windows exec just starts a brand new program but doesn't reserve the capability that you can copy the file the values, including the open file descriptors in your parent process. So what happened in exec is saying that we have these pieces of a code, right? So when you call fork, you are going to duplicate the process as we used to be. However, when you call exec VP, your code section as well as your the whole virtual memory space will be overwritten. So originally what you have will be gone, and you will see a new program as the output instead of the original output. So that's the power of exec. So with this fork, exec and exit, I believe you probably have a good idea about how to write your own shell. So and we want to implement the redirection in a shell as well. So saying that if we want to do we want to execute a program like A and pipe it redirect its output to b.txt, right? What will happen is that first of all, you fork a trial process to execute the program A, and the fork code would open the file b.txt, and the fork code would duplicate the file descriptor, and the fork code assign the b.txt to its standard input and output, and close the b.txt, and finally you can execute the program, right? So that's the whole process, right? And the whole idea is that we fork a new process, and the new process receives the b.txt as the argument, and we open the file, duplicate the file descriptor, reassign the file descriptor to the standard input output, so that everything that the later program outputs would go into the b.txt, right? So that's the whole idea of how to implement redirection in shell. So with that, right, you can what will happen is that, well, you can write a simple shell like this. So first of all, we keep detecting if the user have a new command for us to execute, and if there is this one, right, we would open we will open a file called b.txt, and remember this is within the child process. So the parent process won't do that, right? And then we duplicated the file descriptor, and we close the current file descriptor, and we copied this one to std out. And the reason is because later on, remember the exe CVP will overwrite your memory space. So if you don't make a copy here, the file descriptor will be flushed to 0, and you won't be able to reserve the value, the open file descriptor, the value of the file descriptor of your of the b.txt. So that's why here you have to duplicate the open file descriptor and make it the std out, and close here, and then you can safely flush your virtual address space like what we are doing here. So that's the whole idea of implementing the shell, right? So and the reason why we don't do this in the shell or say the parent process is because you want your shell prompt to be react to the next input as soon as you can. So here we only do this this pieces of lines in your child process instead of the parent process. So if you don't trust that this pieces of code will work, let me show you the demo. Right. So here I have the my shell. So this is the content of my shell, right? So, well, of course, I have some more features here, but this my shell is, well, this my shell is actually not implementing the redirecting feature, but it gives you an idea that we can indeed implement our own shell through user space programming. So everything here is user space API. And what I did here is that, well, I use another, I use a command parser that parses the command and try to get rid of some of the spatial characters. And if you type an exit, then the shell will be terminated. However, you can definitely execute this program with execvp. So now let me make everything here. And well, to show you that we can execute another user program, I create another user program called noise. And my shell is just a simple user program. As you see here, it's not owned by root, it's owned by tseng, right? So now I'm executing the program, my shell. So it changed my prompt in a command line. And I can use that to run another program called noise. And as you can see, well, the noise program runs as it's supposed to be, and it's still printing out exactly the same 14 lines of animal noise. And when I when I input exit, it goes back to my original shell, right? So this gives you another evidence that, well, you can definitely implement shell in just user space programming. So shell is by no means a kernel feature provided in Unix. So that's the demo we have. And sometimes saying that, well, I have a pretty, I would say, careful parent. And sometimes you want the parallel processing because you want, sometimes you want to create multiple processes because you want to perform some kind of parallel processing. So maybe your parent program wants to wait everyone finish before we can exit. So the wait and wait PID functions are used in this way. All right. So although we say we have the wait, right, but that's only useful when well, that's assuming that all your process will terminate it. But sometimes your process would exit, but exit earlier. Would be executed abnormally. So sometimes your process will be entering into the zombie state, which means that they cannot be killed normally. And zombie state is probably the worst case because your PID will remain in use. However, we should, when we try to manipulate those processes, the zombie process is definitely one thing we should avoid. And there's another case called often. That's when the parent process exits before the child process. However, that's not a very big deal because at some point in your operating system, there will be an init process try to collect this orphans, and when this child process without parent process are adopted by the init process, this is called adoption. And at some point, we will periodically cause wait to get this child process collected. So often is now less of an issue, but sometimes you will see in top that, well, some of the process becomes zombie because their process exits abnormally. So those are the states that you might be aware when you are manipulating your UNIX system. All right, so far we have done with everything that you should know about the UNIX at this point. And again, well, another big part of UNIX is the file system, which we will definitely mention later in the class. So don't worry about that. So now let's talk about another important operating system that we are going to discuss in the design philosophy of operating systems. So that operating system is called Mach. So again, so we have Unix. Why we have Mach? Don't you mind to spend 90 seconds to think about why we have Mach? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so it's definitely a question that I would like to have you guys going into group discussion. So now go ahead and do it. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now I'm inviting groups of you to share your thoughts. Okay, I got Yunze. Yunze.
All right, so our group was struggling a little bit, but we pinned to one answer, and it's a correct answer. So we think 3 is correct. The answer 3. So
Okay, 3 are correct. So what are the 3?
Oh no, we choose B, but we think the 3 in the following statement is correct.
Okay, so there is only one you guys don't agree. Which one?
And yeah, so the first one, it says modern UNIX system. So the paper basically focused on old Unix systems, so that one definitely crossed out.
Well, so when we say modern, right, it's actually the modern in 1986.
Yeah, but
okay, but anyway, so you don't think the interface, you think the interface is already consistent?
Already consistent for me, because when I first begin choose this, I also choose 2. I think the first one and still the one is correct, but yeah, but after group discussion, they say it's modern, so modern is definitely not.
Okay, so what about the second one?
The second one, it says can only be provided. So the word only, it's to absolute. And yeah, and so the second one is not correct. By no means is correct. And then the fourth one, it says network communication not protected. That's not a motivation, I guess.
Okay.
Yeah.
Emmanuel.
There was an entire section in the Mach paper about network communication and security. So I believe that 4 is correct. Even though we didn't have enough time to finish our discussion. So I believe 4 is correct in my group.
So what's your group's consensus? Because both you and
yeah, that's the thing. We didn't have enough time to finish discussing.
Okay, but at least you guys. So from what I can hear, at least your group think 2 and 4.
3 and 4. 3 we know for a fact is correct because there was a passage in the paper that
3 and 4
multiprocessor.
Okay, now let's look at Xing Yun. What do you think?
Hello, I'm from Team Blue, and I think the answer is E. Both 4 options are right.
Okay, both 4 options are right. And how does you thought about that? Why you thought about that?
And the first part we can find in the paper is in the first chapter introduction. The last paragraph in the introduction, we can find the paper said, and let me check it. Yes, this paper was providing a basic support for large general purpose multiprocessors, smaller multiprocessor networks, and individual workstations. I think this will take a proof of the option 1 and 3. Yeah, because Unix didn't do the job for this, so Mach will provide the consistent interfaces and
yeah, but can you give an example
process
where the Unix system does not provide a consistent interface?
I think Unix system has some. I can't clarify it very fluency, but I think let me talk about option 2 and 4 first, then back to this part. Okay.
Definitely.
Okay, and The option 2 can be found in the chapter 2 design and in extensive kernel. The second paragraph, it mentioned which in the past could only be fully integrated into UNIX by adding code to the operating system kernel. So I think the option 2 is right. In the fourth option, it says network communication is not protected, and in this paper we can find a big part of capability-based interprocess communication, which is used to solve the security, which is used to improve the security of network communication.
Okay.
So I think the four options are right.
Okay, so how about the third one?
Because I found the purpose of Mach is supporting the multiprocessor. So I think the third option is right.
Okay. So, okay, cool. So thanks for your sharing, but sounds like we all have some kind of confusion about why there is well, we thought UNIX is great, right? But why there is Mach? So let's look at this, right? So, well, some of you think like, well, we keep saying that UNIX has unified abstraction, but we also mentioned, remember the word moving target, right? So UNIX, in the very beginning, it doesn't support network, right? So everything about network, everything related to that kind of stuff, it's later on added. And when people edit, we will have different ways of doing it. And another thing is that, well, in the very beginning, we are just running a few individual processes. We were not thinking about having them communicate with each other. So everything that's trying to communicate becomes something that Unix later on added. So for example, if I want to have different processes that can talk with each other, there are many ways I can do it, right? So here, let me give you an example, like pipes, like this one, right? You can have saying that you can execute a program A, and its output will become the standard input of will become the input of another program. So that's one way you can have inter-process communication, and you can use PTYs to communicate between processes, and you can use signals. So, for example, do you remember that one process can return its status to the parent process by using signals, or I can use some kind of signal interrupt to signal another process. So this is also another way of inter-process communication. Network sockets, right? You can definitely write two socket programs running on the same machine with the same IP, listen to different ports to communicate with each other. So if you want to have two processes talk to each other, actually you have 4 different ways. So is this consistent? The answer is no, right? So Unix doesn't have consistent interface, at least for inter-process communication. And many of these are not protected, and there's no consistency and location dependent. For example, for sockets, right, it's pretty much well, for sockets, well, so for this mechanism, right, like pipes, you won't be able to use that mechanisms on 2 programs running on different machines. And sockets, you can use it to run on different machines. So it depends on where your processes are, right? And signals, again, you cannot use signal to communicate on process on different machines. So they are location aware, right? So those are the stuff Unix doesn't give you a consistent interface, and you have to consider all this of this before you can decide before you can decide what to use. So first of all, Unix doesn't have a consistent interface. Another thing which the paper was mentioning is about the usage of multiprocessors, right? So in the past, multiprocessors, they are not that that often. But now you know that multiprocessors are everywhere. So look at the design of your multiprocessors, right? Like this is an Intel multiprocessor, and you will see you have a bunch of cores within the same die, and they all have a shared memory. So if you redraw the idea of chip multiprocessors or processors on different machines, you will see at the end, it all falls into the picture that each processor has a core, a few registers, its own local memory. But at some point, they are going to share their data physically, right? But thinking about your process abstraction, what your process looks like is that it just duplicates everything, right? So in your for some reason, I cannot find my slide. Anyway, so the process abstraction, if you remember what we have in the past, right? The process abstraction for every program, you just have an individual virtual memory address space that's not shared with each other. However, if you look at the hardware design, you are actually able to share your physically share your main memory at some point. So this doesn't, so simply the process is not really reflecting the hardware we have. So you definitely need a new abstraction in addition to threads, to process for your system, right? So that's another reason why we need a different system, right? So first of all, if we look at this question, right, modern Unix systems do not provide consistent interface, right? We already showed this through IPC, and the process abstraction cannot use multiprocessors efficiently because ignore the fact that we have the shared memory, right? Network communication is not protected for sure, right? And because it was not part of the original Unix abstraction at the very beginning. And the second, system level services can only be provided through full integration of the Unix kernel. That's also true. Not because part of the reason is that if you read the paper says that. And the other thing is that thinking about the unified abstraction in Unix, everything is file. So it means that any system label and any file system manipulation require going through the kernel, right? So it also means that if you have file as your unified abstraction, then everything that relies on the file abstraction will have to go through the kernel space. So it means that, right, system level services, they all have to be provided through the kernel. So every time you want to add a new feature at a system level, meaning that you have to manipulate the file abstraction and you have to go through the kernel. So everything here are reasons why we need a new operating system instead of Unix, right? So, and why Mach, right? If you read a paper carefully, right, they say, well, for providing basic support for complexity of distributed architecture, it becomes increasingly important to the original Unix model of consistent interfaces, right? No consistent interfaces, and there's clear need for underlying system to be transparently extended, right? So it implies that everything right now must be fully integrated Unix by adding code to the operating system kernel, right? So, and the Unix-like system for the new architectures and the new architecture, they are talking about general purpose multiprocessors and small networks and individual workstations, right? So those stuff are the reason why in the very beginning. Okay, Josiah, do you have questions?
Yeah, you can keep talking, but I did want to ask a question about Mach.
Okay, so can you ask?
I was just going to say, I know it has kind of fallen by the wayside, and that the current Linux kernel is still monolithic, but does Mach sort of live on with like BSD and
okay, so
Mac OS?
So first of all, the Linux kernel is not monolithic.
Oh.
Does that address your question?
Yes.
Okay, so Linux is not monolithic kernel. We will talk about that later. Probably not this lecture, but the next lecture.
Okay. Thanks.
Okay, cool. All right, so Mark, okay, is proposing to address all these shortcomings of Unix, right? So, maybe starting from tomorrow, it will be politically incorrect. But what I want to say is that the whole idea of why we want Mach is because we want to make Unix great again, right? So that's the whole idea. That's the whole idea of why you want Mach, right? So, so now I want you to connect the whys and the whats that are proposed in a paper. So in Mach, they propose quite a few things. And I want to ask you why they propose these things. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now let's go into the group discussion to look at to see what do you guys think in a group setting. All right, wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now let's look at what's after discussion. So after discussion, all the answers converge to a single one. So I'm inviting one of the group to raise your hand. Okay, so I have Rogelio. You are also a good gamer. So what do you think?
Thank you. I think the answer is D. Three of those are correct.
So only one of them that is not correct. So which one don't you guys agree?
We don't agree with number 4.
Number 4.
Right.
So what it actually
because in the paper, I mean, at least in what the parts I'm looking at, it does state information about messages and ports, but the reason is that I don't think it's because it's repetitive but confusing mechanisms. And that's kind of the consensus we reached.
Okay, other thoughts. So I have Josiah. You are also from the red team.
I'm from the blue team.
Oh, well, you are from blue team. And okay, what do you think?
We thought that 1, 2, and 4 were correct, but that 3 was not correct because OS extensibility was a big selling point for Mach, but we didn't think it was related to the kernel debugger.
Then what really makes it the OX more extensible in Mach?
I think it's like the modularization of the operating system.
Okay, cool. So that's actually pretty true, right? So one of the reason Mach is, so actually Mach is using a different type of kernel called microkernel. So which we will talk about later because we are almost running out of time for today. But the third one that is not correct. And for repetitive and confusing mechanism, and in fact, messages is messages and ports, that's the unified inter-process communication interface that Mach proposed. And they also use the message and ports to perform its network computing. So everything that needs communication end up goes to the message and ports abstraction. So that's something Mach proposed to address the repetitive but confusing mechanism, but also focusing on the support for the network in Mach. So we will talk about this later. And thanks you guys for sharing. And the answer for this question, I would say it will be 3. And the right thing is that the object kernel and object-oriented design in Mach actually promotes the extensibility. So so we will continue talking about Mach and the thread abstraction in the next lecture. But before you leave the classroom, again, well, this is Thursday. I will give you guys will feel relieved because we don't have reading quiz. The next reading quiz we'll do next Tuesday. I will pull up the reading quiz no later than tomorrow. And again, well, we will have projects in group of 2. And some of you are asking, well, why can't you release the project as early as possible? I just want you to give us some kind of understanding because although I keep saying us, but the actually staff who is hosting this class is only me. So there is no TA for this class, and the only staff that we have for this class is just me. So so I really spend a lot of time trying to debug the project and make sure that it's doable, right? So if you don't want to have a project that has a lot of commits after it's announced, give me some more time. And if you I'm trying my best to release the project as soon as I can. But if unfortunately I cannot release the project by the end of the week, at least I will give you a set of readings that you can start with. But at this moment, it's most important for you to find your group. And also, I have an office hour tomorrow, 1 p.m. to 3 p.m. If you have any question regarding to this class, regarding to any material that you understand, it's the right time for you to ask questions. Other than that, enjoy the rest of your day, and I hope you have a better day after today.
You found the lies I built around me, made up some brand new ones about me. Baby, I love the way you're looking in this good light. I love you 'cause I don't love me. I love you 'cause I don't love